Okay, so let's start. Hello, everyone. Welcome to episode 12 of Warsaw.ai. Today we'll have three great speakers. Our first speaker is Róża Chojnacka, a researcher from Google Research from New York. And she will give a talk titled SpeakerStew, Calling to Many Languages with a Triaged Multilingual Text-Dependent and Text-Independent Speaker Verification System. So looks interesting. And the second speaker will be Tomasz Danel from Ardigan. And the title of his talk is Into the Unknown, How to Minimize the Risk of Models Making Wrong Decisions. And last but not least, the first speaker is Dr. Jakub Nalepa. He will give a talk challenging Sens.AI towards CE-marked deep learning software for brain tumor analysis. So as I said, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. If you have any questions during the lectures, you can post your questions on our chat. So after each talk, there will be a Q&A session. Maybe some speakers will also prefer to just have some interaction with you, so they can also announce it. So we hope that you will enjoy this event. And I think we can start. So Róża, welcome. Thanks for accepting our invitation. The Zoom is yours. I'll just stop sharing my slides and we can start your presentation.
Awesome. Okay. Hello, everyone. Do you see my first slide?
Yes, we can see it.
Okay, awesome. So this is Róża from Google Speech team in New York. Thanks to COVID, though, I've been working remotely from Poland for almost a year now. I'm honored to give this talk to Warsaw.ai community, and I thank Paweł for the invitation. You can ask me questions during the presentation. I like some interaction, and after, if there's time. A codename for the project is SpeakerStew, and I'll address scalability and performance problems when it comes to generalizing monolingual speaker models to multilingual ones. This work was accepted to Interspeech, which is an international conference on spoken language processing. Let's start with a use case and terminology used in speech. As far as I know, this is the first speech talk among Warsaw.ai events, and speech is less popular than other domains which use deep learning techniques such as computer vision. So excuse me for like basic introductions. Okay, so on a high level, speaker recognition is similar to face recognition. We train a neural network nowadays. In the past, we used different techniques. And later enroll users which we'd like to recognize. At runtime, when we receive a speech sample, it's compared to those registered before. And if it surpasses a predetermined threshold, we claim that the speaker was recognized. Thanks to speaker recognition, we can personalize the results at Google. In a daily life, you've probably been given an option to use your voice to verify your identity in telephony computer systems. Okay. The core technology behind speaker recognition is what we call the D vector. Sometimes it's also called the embedding or the voice print or the fingerprint. Given an audio, we use a multi-layer LSTM network to generate a multi-dimensional vector, D vector, that represents the voice characteristics of the speaker. Yeah, so it's similar to face detection. Okay, one more intro. In speech community, we differentiate between text-dependent and text-independent systems. text-dependent system was developed to recognize a speaker who says some predetermined keyword. In the case of this paper, it's OK Google and Hey Google. It varies slightly between languages, but it's a tiny difference. Okay, just in pronunciation, like each language uses the same keyword. Okay. On the other hand, text-independent system doesn't have such constraints. It should recognize the speaker on any utterance. You may ask why we have both text-dependent and text-independent. And the reasons are speed and accuracy and model size. Like the smaller text-dependent model can be like installed on any mobile system, for example. With this intro out of the way, let's dive into the details of the paper. Speech technology is evolving rapidly in the recent years. Thank you, deep learning, and thank you, users globally. So it's hard to maintain dozens of monolingual models and support new use cases. On top of that, it's challenging or impossible to acquire data for new languages. Hence, it became more and more important to create models which can support not only multiple dialects, but also multiple languages, and maybe eventually just have one universal system. I can add from myself that in ASR, we not only have one model per language, but there are multiple models which support different use cases. So it's very, very hard to maintain everything. And in the next slide, let's uncover what questions I wanted to answer with my colleagues in this work. First, we'd like to explore whether we can build a multilingual model without a loss on quality. Then is it possible to even generalize to languages which data we didn't use during training? Also, would it be easier to build multilingual text-dependent or text-independent system? And finally, since training a multilingual model saves an order of magnitude of GPU energy on training compared to training one model, so we wanted to explore whether we could also save energy in production while at the same time maintaining performance. So we'll make some I'll make some proposals regarding this issue later as well. Before I dive to experiments, let's take a quick look at the data we used. It's coming from different vendors across the world, and the volume of data differs significantly. You can see, for example, that we have close to 40,000 English speakers from various countries, 3,000 German speakers, and but only 100 Polish speakers. Overall, we had vendor data for 46 languages. To my knowledge, it's the first paper to conduct experiments at this scale. And previously, it was magnitude less. I didn't want to clutter the slides, so showed only a small selection of languages. We trade 20 text-dependent models and 20 text-independent models. 12 of those are monolingual, high resource languages such as German, English, and Spanish. Another models we trained are monolingual low resource languages or low tier languages, which were not prioritized before. And on top of that, we trained multilingual models. Multilingual 12 model uses a union of data from 12 languages, and multilingual 46 uses data from all 46 languages. We trained both so that we can compare how well Multilingual 12 model generalizes to unseen languages such as Arabic, Mandarin, or Polish. Any questions so far?
I think everything is clear. I don't see any questions in our chat.
Okay.
So,
Awesome.
Yeah, there's one question actually from Camille. With text-dependent models, do language matters a lot?
Yes. Actually, I will reply to this question with my next slide. So as part of data, phrases are fixed anyway. What's the quality of data? Is it an issue? Okay. So let's look at this slide. It's like data analysis. So we'll see cross-language evaluations on the diagonal. You see monolingual system evaluated on the same language. Outside of it, the diagonal, we have cross-language evaluation. So let's say we want to deploy a model in Portugal, and you can see that. Let's take a look at the top, at the right column. The German model would be the worst choice, and the Spanish would be the second best after Portuguese. So there's Spanish performs 50% worse, and depending on your criteria, it might be good enough. And I can see a scenario when we deploy a Spanish or English model in other locale. But if we want to be very sensitive about mistriggers, then we want to perform the best. And yes, so that's why we wanted to explore a multilingual model instead of using Spanish in Portugal. And the difference, so difference ranges from 300 up to even to 300% worse. What metrics are used for evaluation? I used EER. It's called equal error rate. This is an error rate which determines the threshold values when false acceptance rate is the same as a false rejection rate, and the lower the better. In production, we might want to optimize for false accepts, but EER is standard speech recognition metric I've seen in papers. What's the quality of data? Is it an issue? Yeah, the data comes from I forgot how many speakers. What was it? 126,000, and some of it was put under quality control, but well, it's not perfect, but yeah, it was good enough for us. Okay. Next slide. Okay. So on the left side, we can see high resource or tier 1 languages. On the right side, we have low resource languages where we don't have data or we cannot use the data. In both, I highlighted the best score. Unsurprisingly, there is a huge improvement when using multilingual model on low resource languages such as Polish. Interestingly, Multilingual 12 scored slightly better on Polish, but it's a negligible difference. So Multilingual 46 had some Polish data, but maybe it wasn't enough to make any difference. I didn't do any rebalancing of the data. It was just the union, and the model architecture was the same. I would just check that it has high enough capacity to train multilingual model with all the data. Okay. Of course, there are some languages which need to be addressed here, such as Korean, but it's outside of the scope of the paper. And when it comes to speech recognition, I've seen that upsampling helps. Also, using I don't know, a deeper architecture, or fine-tuning, adding language ID as one whole encoded vector, but I haven't addressed this in the paper. But yeah, there are options to make it better. Okay, so far we combined languages into one model, but how about combining text-dependent and text-independent system? Turns out we can improve scores further by combining them both. We can select such an alpha such that the linear score, alpha times TD score plus 1 minus alpha times DI score, yields the best result. And we've chosen such alpha for each language separately. Okay. Any questions so far? Oh, I should speed up because it's already 6:20. Okay. So when we compare text-dependent and text-independent, the ER score is the lowest. Let's bring questions again. We can answer our first question that yes, it's possible to use a multilingual model instead of monolingual ones, and Multilingual 12 generalizes pretty well to unseen languages. And now let's focus on the second part of the paper, which is how to reduce latency during production. Okay. And it turns out that our proposal is to use the TI system when we are certain that it's a target speaker. Thanks to this approach, there's no need to wait until user finishes the query, and we can process the results much faster. Okay. The challenge here is to choose good thresholds. We need 2 for lower bound and upper bound. Also, should we choose different thresholds for different languages? Let's answer this in the next section. To find good thresholds, we did a sweep with sweep or grid search, however you call it. So we selected lower thresholds and upper thresholds and computed text-independent system trigger rate. These are represented by contour lines. It means that if okay, let's look again here. So if the score is below this threshold, then we are confident that the speaker is an imposter. And if it's above the threshold, we're confident that this is the speaker we are trying to verify. Okay, and in the middle, we are not sure. So we will use a linear score combination of text-dependent and text-independent system for these uncertain cases. Okay, so here are the results, and we want to choose the lowest ER. So it's gray, and we want to choose such lower and the upper threshold, so as the TI trigger rate is the lowest. Like by looking at this heat map, I can see that the optimal TI trigger rate is 27%, which means that only for 27% of the queries will be using both text-dependent and text-independent system. And otherwise, we can return results very fast with text-dependent system. And yeah, if you look at the graph, the lower threshold for this case is 0.23 and upper 0.65. Okay, thanks to this. Okay, let's see how much latency is saved. Average duration of the keyword portion of speech is 700 milliseconds. This is how long it takes to say "Hey Google," and the average duration of the query is 3 seconds. And also 3 seconds is optimal for recognizing the speaker. After that, we don't see much benefit. So with triage, the expected time to verification is reduced by 60%. Thanks to knowing the speaker identity in advance, we can fetch contextual information such as I don't know, contacts, playlists, or search history before starting to process ASR. ASR stands for automatic speech recognition. So to wrap up, can we use a single model to generalize across SIM languages? And the answer is yes, it's unreasonable. We can start from like some of the languages and fine-tune the rest. Then can we generalize to low resource languages or even unseen languages? The answer is strong yes. If we don't have another like better baseline, and it's much better to like combine data from all languages. Then are there opportunities to reduce energy while maintaining performance? Yes, I can. Yeah, I show this. First, we train like less models. Second, like we use like the triage, and that saves us both like energy and latency. And finally, can one model rule them all? Yes, it's possible, and I can say that yeah, we use multilingual models in production. Okay, thank you. Any questions?
Okay, thank you, Róża. Thank you very much. It was very nice and interesting presentation. Are there any more questions to Róża? There's a question from Kamil. Are there any works to make the model robust against things like cold and other situations which might affect our voice?
Oh, oh well, this is very interesting. A very interesting question. Yeah, so ideally, like this is important not only for training, and when we collect training samples, we ask like vendors to like record them in different environments. So for example, when we wanted to make sure that the model would perform good in cars, we asked them to like turn on the fan, to turn on the TV, so that there's some noise. And on top of that, we apply like data augmentation techniques. So we usually it's yeah, it's like adding voice, but we don't want to modify like some speech characteristics. So for example, I don't want to change the pitch of my voice. Like we've seen in the experiments that the results were worse when we change the pitch or the like how fast somebody talks. Yeah, we haven't checked the code. it might be like unusual situation, I think. I don't know. For me, it worked fine when I had a code.
Okay, good. Fair enough.
That
Yes,
one more question. What if the speaking tone of verified speaker and guest speaker are same? How can we overcome that problem? Like tone is, I think this is like when we built a speaker embedding, we ask the user to tell the query 4 times, and then we average that, and it should be pretty robust to this use case. And there should be like more voice characteristics than tone in the embedding, but of course it's not like bulletproof. I still have some work to do to improve further. I can say that the big problem is when differentiating household members, because they have I don't know, like mother and daughter can have a similar voice. And yeah, it's challenging, and like we don't have data because it's very private. So yeah, there are many like long tail problems.
Okay.
Yeah, thank you for very good questions.
Okay, great, thank you. Maybe just one more question. How do you think, what might be some interesting research directions in this domain, or are you aware of some other research teams working on similar topics? Because I understand that for sure you need a lot of data, and in case of Google, it is possible to just have a lot of data, but would you recommend some interesting research directions for some scientists willing to start working in this domain?
Right. Actually, for Google, data becomes a huge problem as well. Like this research was done only on vendor data. Like it wasn't like user data. And from, I think, last year, we explicitly asked users whether they want to like donate data for training. So indeed, like it's a big problem. And what I've seen around me is that people experiment with unsupervised models, for example, Back-to-Back, that was shared by Facebook research team. And another big area is like training on device or other like privacy centric ways. Yeah.
Okay.
So there's that.
All right.
Yeah, but unsupervised is
unsupervised learning. Okay.
Bigger.
Yes, it's reasonable. All right. I don't see more questions from our participants. So Róża, I know that this work will be also presented at the InterSpeech conference. Is this correct?
Yes. Next month.
Next month. All right. So yeah, good luck for this presentation, and thank you once again for this very nice talk. And I think we can.
Thank you.
Yes, I think we can proceed, and we can invite our second speaker, Tomasz Danel from RDGen. So Tomasz, if you're ready, you can start sharing your screen.
Okay, thanks. I'll share the screen now. Yeah, it should be visible now.
Okay, yes, we can see your slides now.
Okay,
thanks.
Great. Yeah, so hello, my name is Tomasz Danel, and today I want to tell you a few words about uncertainty models and how to estimate reliability of the predictions. So this is who I am. I'm a data scientist and product owner at RDGen. I'm also a PhD student at Jagiellonian University. I am also a member of machine learning research group GMUM. My research interests are deep learning, computer-aided drug design, and computer vision. So I mainly work with images and molecular graphs to discover new compounds that can be used as potential drugs. And this is exactly the topic of the presentation, is how to make sure that the objects that we generate are reliably predicted by machine learning models. The agenda of my presentation is, first I will discuss the uncertainty estimation in automated scientific discovery. Then I want to tell you about data splitting and how important it is to make a correct choice with the way we split the data. And finally, I will present two approaches to assessing model reliability. These methods are conformal prediction and Monte Carlo dropout. So starting from the topic of automated scientific discovery, when you build a machine learning model to predict your data, to predict some properties of your data, you have some amount of the data that you can work on, and you try to create models that can predict properties on this data. So these models should work well with the data you have. But what about other data that are there in the real life? I mean, you have some set of data examples. But when you try to create an AI program that will generate new examples, they will probably end up out of the distribution. So they are out of your data sandbox, as I call it. And these models that you created for the data you have, the data that can be accessible online, or the data you collected and have internally at your company, these models may not work well with the data that are out of the distribution. But it's still important to have some tools that can reliably assess the quality of created examples. If you create new instances by generative models, or if you have a data that you just want to assess with your models. So I will focus on chemical examples, but all these models that I am talking about today can be used in any data. So this is just an example. You can apply it to any fields you like. Probably you find something interesting in these models as well. So in my example, the sandbox is our internal data set of chemical compounds. We have a set of compounds that were tested for biological activity, for example. And when a new data arrives, when you have a new compound, it can be a compound designed by medicinal chemists or a different laboratory, and you want to predict the biological activity, for example, of this compound. It may be very difficult if this compound is nothing similar to the compounds you have in your internal library. So your models may fail to predict the compound activity, for examples. And the problem exactly here is that the probabilities that are returned by machine learning models are not certainty estimations. So the probability of a class that is returned by a classification model does not correspond to the certainty of the model. And many out of distribution samples may be predicted as one class with high probability, but in fact we don't know if this data point should be assigned to this class because it's nothing similar to what we have in our data. So how to estimate that and why this is a problem? Suppose that you have a compound that your machine learning models predicted as a potential drug candidate, then you are happy about it and you put this to tests. So you run biological tests in a lab, you pay a lot of money to do that. And if the test succeeds, you proceed and spend even more money to run the tests on animals or start clinical trials. At some point, you want to file a patent as well. So it costs a lot of money. And at the end, the animal can be very unhappy about your compound. So it can be toxic. And you already spent a lot of money. It can be in millions of dollars to test your compound that was wrongly predicted by the model at the start. So the important thing here is to fail fast. So to have models that immediately can tell if the predictions are certain or not. If the prediction is, if your model predicts a compound as active, but is not certain about the prediction, you save a lot of money on the biological testing. You can go just with other compounds that have more certain predictions. So this is the motivation, and now the first part of how to address this issue with unreliable prediction of machine learning models. The first step is data splitting. So this standard approach to data splitting is just to take all the data you have and draw a random sample for testing. So this is a standard split. Some data goes for the training, and some data randomly chosen go to the testing set. And this is the standard approach, but it has some problems, especially when you try to run a scientific discovery where you generate new data that are out of distribution, because this data split does not answer your scientific or business question. So if you try to create a model that predicts biological activity, your question is if it can reliably predict compounds that are new, that are modifications of what exists now, but it can be very different to what you currently have. So the answer to this question, how to predict new chemical structures or new chemical compounds, is to narrow down the data set to a subspace of compounds that are very similar to each other. So in other areas, it can be also applicable. You may have a data set and some features of data points in this data set, and you can narrow down to only these data points that have some specific feature. And this is your training set, and then you can see if your models tested on data points outside this subspace also predict with high accuracy. So this also is in some sense estimation of the uncertainty. It's based on geometry. So you have data points, you have some similarity measure, and you try to create a data set that is consistent with respect to some feature. And then the further examples are from your subspace, the less certain they are. And in the field of chemistry, an example criterion can be structure similarity. It's called scaffold split in this domain. and it works on chemical structures. So chemical compounds that have the same substructure go to the same fault or the same subset. So for example, in the testing set, you don't have the structures that you may have in the training set. And then the accuracy that is returned by the evaluation of your model is accurate for your specific scenario. So this is exactly what you wanted to test this model for. And another example of data split that answers your question. In this case, this is stock data. So the question may be, will my model work for the future data? So yeah, because if you use a random split, it's just nonsensical, probably, because you want to predict well the data that comes in the future to predict if the price rises or goes down. So the data split here, that is the answer to your question, is the time split. And here for the training, you take the data up to some time point. And for the testing, you take all the data that is after this time point. And as you can guess, the same works for chemistry. We can split our compounds to two sets. One is a set of compounds that were synthesized earlier or published earlier. And the second set is a set of compounds that were synthesized later. And in a typical drug discovery project, when you have some compounds and you try to come up with better compounds, more active or more soluble, you base your decisions on all the previously discovered compounds. So it makes sense to choose a time split so that each new compound is somewhat dependent on the compounds you already know. And the second part is how to use some specific models for uncertainty estimation. Here we discussed the data splitting. It can help to get better alignment between your accuracies and the real life scenario. And here is the one of the models that can help you estimate how your predictions are certain. And in this part, this is the part where math goes in, but this is very simple method, so the math is very simple here. The first method is conformal prediction. It can help you with the problem that is described in this slide. So as I mentioned already earlier, machine learning models are typically not well calibrated. This means that if you have an input X and a true label Y, a predicted class Y prime and the corresponding probability P prime, then for all P in range 0, 1, it is not true that if the predicted probability is P, then you predict the correct class with probability P. And in other words, we expect that among all data points predicted as Y with probability P of them actually belong to this class. So this is typically not true for predictive machine learning models. This is the description of the method. So what this method requires is first, you need to define a non-conformity function, R, and this is a function that describes how strange a data point is. So it should measure the similarity from the training set, and it can be based, for example, on the model predictions. So you can define R as, for example, 1 minus predicted probability, and it will measure how strange this data point is. And in the next step, you can calculate p-value. So you create a calibration set. You need to have some calibration data to calculate p-values. And if you have calibration indices I, then you can calculate p-value for new data X and Y. So the features and the label as in this formula. And this formula says that that p-value, to calculate p-value, you count how many data points in the calibration set are more strange than your new data point. So this is this part. I don't know if the pointer is visible on my screen. So this conditional part is about counting how many calibration examples are stranger than your new example, and it is divided by the number of data points in the calibration set. So p-value 1 means that all the data points in the calibration set are if it's 1, it means that all the data points are stranger. So this is indication that this new example should belong to this class that you consider, the class Y. And then the most interesting part about conformal prediction is in this formula at the bottom. This is the final prediction that you have. So instead of predicting one value or one class, you predict a set of classes. So this is not a point estimation, but a set estimation. And your prediction is all classes that have p-value greater than your significance level that you can have decided on before the experiment. Yeah, so this means that in this set you get all classes for which you cannot reject the hypothesis that your new example does not belong to this class. And by the way, there is a variant of this method that works on training data instead of calibration data, but it's more tricky to do that because you need to retrain the model again and again. So here is an example how this method works. Here we use as a non-conformity score, we use 1 minus predicted probability of true label. We have significance level 10%, and we have clearly a black box model that predicts toxicity of a compound. And we have a calibration data on the left, which these are compounds that are toxic or non-toxic. We have a probability returned by the model, this black box model, and non-conformity measure in the last column. And suppose that we have a new compound that is predicted as toxic, and the prediction probability says 45%. So the first step is to calculate non-conformity score for both classes. This is 1 minus prediction, so you can easily calculate this for both classes. And in the next step, you can calculate p-values. to do that, you take non-conformity scores and put it somewhere in this ranking. It goes here between the first and second example for both classes, for toxic and non-toxic. It lands here at the second position. So p-values, to calculate p-values, you need to count all the examples that are presented above this line. So this is the same for both classes, and the prediction is a set which contains toxic and non-toxic labels. So it really means that we are not certain about the prediction, because the model says that it can be toxic, but it's also probable that this new instance is non-toxic. So this is not a decision that tells it's one class. It tells it should be both classes. So this is very uncertain prediction. Here we have another example with different probabilities, different non-conformity scores. And in this case, for different classes, we end up in different places. So p-values are 0 for the toxic class, and for non-toxic class, it's higher. And here, as conformal prediction, we have a set that contains only one class. So here we have a certain prediction, and we are certain that this new item is non-toxic. And also there exists a different variant of this method that is conditional on the label, but probably we don't have much time for this variant. So just to mention that this method is constructed so that it accounts for imbalance in the data. If you have in your calibration set less examples of one class, this is the better choice. And here, where you calculate the values, you calculate only p-values based on examples from one class. So, for example, if you calculate p-value for toxic class, you calculate it only on the toxic compounds in the calibration set. So these examples here are the same as previously in terms of probabilities, but you can see that non-toxic class is predicted less often when you balance the data with this label conditional variant of the method. Am I after the time already?
Yes, we are slightly behind the schedule, so but I understand that you still have some slides, right? Or
yes, I can present it very
think,
briefly.
So if Jakub, our first speaker, doesn't mind, I think we can go on. So let's try to finish in, let's say, 2-3 minutes.
Absolutely, no hurry. Go ahead.
Okay.
Okay, thanks. So very briefly, there is also another method, and these are the differences between these two methods. So in the conformal prediction, we need to have a calibration data set. For this method presented here, Monte Carlo dropout, it uses only the training data, so it doesn't need any calibration. It's a different approach because it's Bayesian and not a frequencies approach. But here you need to have a neural network with a dropout, so it's not model agnostic. And the goal here is to have some uncertainty measure on the new data that are very far from the training data. You expect to have a higher variance. And this method is very simple. If you have a neural network that uses dropout, you already have this estimator. So if you use this network as you do Usually, you get only one prediction, but when you try to run it in a training mode, so you drop some neurons in the layer, then you get different predictions. You get, in some sense, an ensemble of different models and different curves in this plot on the right. And the idea here is that for one data point, you can get many predictions, T predictions, by dropping different combinations of neurons by the dropout. And you can calculate the mean, the predictive mean and predictive variance of this model to get an uncertainty measure. And it does not require anything apart from the dropout that you probably already used to generalize better with your neural networks. So this is the summary. The data split method is very important, especially when you have challenging data with covariate shift, or you try to generate novel data points. And the second point is that conformal prediction is a very simple model agnostic model that you can use to discard unreliable predictions. And if you are a deep learning practitioner and you train neural networks that use dropout layers, then you already have an uncertainty predictor in the form of Monte Carlo dropout, and you can use very easy formulas to calculate uncertainty. Yeah, so that's all from our side. Sorry for the long talk.
Great, this is fine. Thank you, Tomasz. Very nice presentation, and quite interesting. So in fact, I've already came up with an idea how this approach can be applied in my research on traffic signal setting optimization. So in fact, we've already applied this Monte Carlo dropout, I guess, or I think it was called variational dropout, but it's more or less the same. All right, so since we are behind the schedule, I think that we can skip the Q&A part, or if there are some urgent, very important questions to Tomasz, then please post your questions on our chat, and maybe Tomasz can also try to answer later during the last talk. And as for now, I think we can invite our first speaker, Jakub Nalepa from Future Processing and Politechnika Śląska, so Silesian University of Technology. So Jakub, thank you for accepting our invitation. It's our pleasure to have you here, and the Zoom is yours. You can start. You are muted now.
Hi, yes, absolutely. Sorry for that. That's my pleasure. Thank you for inviting and for having me. Today I'll be actually talking about our pretty interesting journey that we had at Future Processing Healthcare towards having a CE-marked software, and that is a deep learning powered software. So that's gonna be yet another deep learning talk. And basically, I'm pretty positive that all of us know that we've been witnessing like big success of deep learning in virtually all fields of industry, and here in medicine and in medical imaging, that's not an exception. And we know that the field is actually blooming. So we have a big number of emerging papers and products that actually try to use machine learning in clinical setting. And what might be interesting though is that probably most of us think of deep learning or machine learning as a part that might, for instance, segment a medical image to extract some useful information, but that is actually just the tip of an iceberg, because if we look at the entire workflow, we can think of the benefits that might be brought into the workflow through using deep learning. So we can observe that deep learning, or in more general, artificial intelligence, might be useful in, for instance, scheduling the workflow, getting higher quality data in terms of images. It might be the images of higher quality, better resolution, etc. Then we have the segmentation of the medical images that help us distinguish some important and useful parts of the image that might be further analyzed in post-processing. And finally, we have yet another blooming area, which is radiomics. Here we just extract a super big number of features that might be useful in, for instance, distinguishing or predicting some outcome for a patient. Today we'll be focusing on segmentation because the Sens.AI, the software that I'm talking about, is focused on segmenting and analyzing the medical data. So if we have a look at a very simple example, we have breast imaging. So we all know that we might be interested in finding some abnormal parts of the image. For instance, this part of the image, even though we do not know if it's abnormal, it definitely looks to be abnormal. And this tissue might be like worth investigating. We might have a closer look at this part of the image to understand what is actually happening to this patient. We focused on brain imaging, so we can have a look at MRI of brain, and that is a very similar story. We have a resonance scan, and we are again interested in finding some parts of the image that are most likely abnormal. So here, if we have a look, we'll spot this area, which is a bit brighter. So the intensity of the pixels that are within the scan are definitely different than other parts of the image, other parts of tissue in brain. And that is very likely that that might be a lesion or a tumor that requires some intervention. And we need to be able to actually track the response of the patient according to a given treatment that is being specifically designed to this patient. And here we are just countering this lesion to understand what is its volume, maybe its area, etc. Because segmenting the image is practically never the final step of the pipeline in the clinical setting. So we might be indeed interested in finding this contour, but after that we are progressing with some additional steps. For instance, we might have a look at bidimensional measurements. For instance, the Rano criteria is just about finding two diameters within the enhancing part of the tumor. So you can observe that in brain lesions, we have some parts that are enhancing in a specific MRI sequence. And we just want to find the biggest diameter. So we have the longest diameter and the perpendicular diameter that is also the longest one. And we are just multiplying those two to have a single metric, a single number that could help us understand what is the response in the patient. And is the patient responding like in an appropriate way, or should we fine-tune the treatment, or maybe we should take other actions? Obviously, if we want to have accurate measurement, we need to have an accurate segmentation in this context. So we are looking at the accurate segmentation of, in this example, the enhancing part of the tumor, but at the end of the day, we always want to have as best segmentation as possible. And that is for a single modality. We might have also different modalities in practice, so we may have some images of the patient that are basically different. We may have some functional imaging and structural imaging that actually contain and convey different information. So you can see that we might have a PET scan and a CT tomography scan that are taken for the same patient, but they are super different. We can see that like the look of the images are very different, and for sure they show different things. We may also use deep learning for trying to, for instance, remove this PET scan and to make the analysis a bit cheaper. For instance, if we could extract some information from just the CT scan, it might be worthwhile to think if we could just drop PET scanning, which might be, for instance, expensive for a patient. Also, we are working on basically 3D images, so we have the entire volume for the patient. Here you can see the example for lungs. We have again two modalities. We have CT on the right and we have PET scan on the left. Again, if we co-register them, we can see that they are definitely taken for the same patient, but they show different things. For instance, we can see the structural information that is better visible on CT scan. So if we want to, for instance, quantify the volume of lungs for some reason, it might be better to exploit that kind of imaging. But often they can go hand by hand, and we can analyze both in parallel to make sure that we extract all bits of information from the patient from that kind of images that are hopefully available. Also, we can go one step further, and if we have the segmentation, we can try to extract some features from the areas that are abnormal, for instance, lesions. And that is going towards radiomics, where we just extract different kinds of features like texture, intensity, maybe shape, etc. So we may build a big feature vectors that should help us better classify patients, or maybe perform prediction in terms of, for instance, the treatment response. Basically, based on that kind of data, that kind of features, we could hope that we should be able to find a better idea what is about this patient. How does this patient actually respond to our treatment? Also, we can try to extract things that are not visible by naked eye, so we can have an additional, I'll say, dimension in our imaging. So we have 4D imaging. In this context, we have a 3D volume for a patient, for instance, an MRI scan. And additionally, we can take those scans in a number of points in time. So we may have a number of different time points where we just scan the patient, and we want to track the way the contrast that is being injected into this patient goes through the tissue. And this tissue is usually, again, the tumors, the lesion tissue within the brain, because, as I mentioned, we are focusing on brain. And based on this contrast flow, we can try to find the curves that will help us visualize and quantify this contrast flow within the patient. You may think that if we have different shapes for this flow, we may have different characteristics, different features within the patient. So this additional, I would say, temporal information might be super useful in clinical setting as well. And also we can try to visualize that kind of data in an image. So we have another, I'll say, feature map that will quantify the contrast flow. For instance, if we have the brighter pixels, we know that the contrast flow was a bit more intense compared to less intense pixels within that kind of parametric map. So at the end of the day, we have a big bunch of different applications in medicine, but there are some drawbacks and traps that we need to avoid. If we have a look at this Nature paper, so we have a top tier journal, we have an AI-based system for breast cancer screening. We may actually believe that this paper is super strong. We know that if you publish in Nature, you should have a very good validation and verification procedure. And that was published in October 2020. And then suddenly this paper came out. So we have a paper saying about the problems with transparency in clinical settings. So we have some papers and we are not able to reproduce the results, for instance, or we may end up having different problems with the paper itself that will actually make it impossible to deploy that kind of algorithm in a clinical setting where we have very constrained setting, because ultimately you look at the patient. So you may affect the patient. You might actually affect the treatment pathway, which is very important. In response, we had, because we can see that the matters rise for this kind of paper, for this initial Nature paper, and the authors responded pretty quickly to this matter, because we want to make sure that our algorithms are fully reproducible. So we should be able to reproduce all the experimentation, and all the data that are within the paper should be easily reproducible, given that you are allowed to get the data that people use in the papers. That is super important in clinical setting, as I mentioned, that if you want to think of deploying that kind of algorithm in practice, you need to be CE marked, which means that you need to go for the certification and you need to sort of proof that you established a good workflow for like building that kind of software, and you had a very good verification and validation procedure to make sure that you will not harm your patient at the end of the day. So again, we were focusing on brain imaging, the same picture as before. You again see the contouring of a brain lesion within an MRI scan. And for clinical setting, if you think of deploying that kind of software in clinics, you need to have something that's called the intended use statement. So you need to clearly say what you're about to deploy in your clinical setting. And that is usually a very short statement that should be easy to understand. It should be impossible to misinterpret this. And in our context, we had just the contouring of our lesions and calculating the volume of the lesion. Here we are also focusing on just one sequence, that is going to be T2 sequence, T2 MRI sequence that's being analyzed. So we do not look at the number of modalities, the number of sequences that might be captured for a patient. We just look at a single modality, at the single sequence from MRI scan. And obviously, I'm pretty positive that most of us would say that probably something that is U-shaped, some unit might be very well fitted to this problem, and we went through the same thing. So we used the UNet-based architecture. It is a bit fine-tuned, but again, it is U-shaped, and we know that actually UNets and currently VNets or 3D units established the state-of-the-art in segmentation in most of the modalities and lesions. So we went the same way. We had a 2D unit. It was done actually 3 or 4-ish years ago. So that was quite time ago. We focused on units, and we wanted to just segment that part of the brain MRI scan. And if we are focusing on brain imaging, we are also need to think about the training sets that would be used for training the models, because we, as we all know, we need some labeled data to train the model and then to deploy it over unseen data, to generalize over unseen data. In the case of brain imaging, we are fortunate enough because we have some data sets that are publicly available, and they are actually huge. We know that there exists a data set that is called BRATS, and we know that that is a well-established data set that has been used for years. This year we have 10th edition of this challenge, because actually that is a challenge where we just submit your predictions for brain imaging, and you can capture your quality metrics for segmentation. So we know that we do have that kind of data, and we could potentially use it, but as always, there are some problems with data. If we look at manual segmentation of medical images, or not only medical, but in this context, medical images, we can see that there are some problems with segmentation. For instance, if we again look at this example, we'll see that if we have, for instance, 7 readers or more than 1 reader, and those readers were asked to find some abnormal tissue, it is super likely that they would disagree with each other. We can see that they have some labels, so we have some abnormal tissue in there, and we have a number of readers that basically disagree with each other. We can see that the common area is in there, but the annotations might be very different, and the area of the annotation might be very different as well. That's one thing. And on the other hand, if we look at medical data captured for different patients, we can observe that there is a big variability for that kind of data. For instance, in children, we'll have very different like look of the images. We can see that the structural information in that kind of data might be very different in, for instance, in children. So if we capture that kind of image in different time points, we will end up having different structures that are presented in the slide. So we need to make sure that our training data and ultimately a test data is very heterogeneous. It should be big, and it should actually allow us to build models that can generalize over unseen data in practical setting. There's also an important problem of quantifying the performance in terms of, for instance, multifold cross-validation, as mentioned in the previous talk. So we wanted to answer the question if this BRAS dataset is of sufficient quality. The sufficient quality is pretty vague, so we are not able to say that it is super high quality, it is low quality. It's like we need to be able to somehow quantify the quality of the dataset. You can observe some examples of ground truth segmentation from the BRAS data. You'll see that the contouring is pretty accurate, but again, we are not 100% sure that the contouring is totally correct within this data. So to make sure that we use good data, we decided to actually make the mean opinion score experiment, which means that we have a number of readers that are experienced and they work in clinics. They have different numbers of years of experience, and we ask them to verify that kind of data. We just ask them to verify the BRAS dataset. They had a very simple scoring, like 4 points, and you can observe that the score 1 and 2 shows that the segmentation is of low quality. So that kind of segmentation would not be used in a clinical setting. You should avoid using scores 1 and 2. And on the other hand, we have 3 and 4, which are acceptable, and we know that those guys might be actually used in clinics to affect the patient. As you probably expect, we had a number of readers that disagree with each other. You can see that if we look at the inter-rater agreement, they are pretty much disagree with each other. So that is unclear if at the end of the day this data set is of high quality, or is it low quality, or is it sufficient quality, or what. So we can see that there are some readers that actually agree with each other. For instance, reader 1 and 5, they are in agreement, but in some cases they disagree in a very massive way. So we need to be we need to make sure that we understand what they actually look at and what is their response in to our question if the data is of high quality. And I might not mention it, but we are not only trying to contour this lesion within the brain imaging, but we also want to skull strip the entire scan. So you can observe that you do not have the skull around your brain. And usually if you do that kind of imaging for a patient, you'll have the skull that is around the brain. So there's another step in the pipeline where we just need to remove the skull that is around the brain within this kind of sequence. And also we utilized a very similar deep model that was also a unit-based model. We trained it over another data, and we deployed that kind of model to skull stripping, so for brain extraction and then for removing the skull from the input sequence. We ended up having a fairly big data sets. We had more than 1,200 MRI scans for brain extraction coming from 4 data sources. We had actually different modalities, so we had different types of sequences in that kind of training data, and we asked 3 readers that are experienced to review that kind of data. So after the review process, we ended up having that number of MRI scans that could be used for training models. On the other hand, we had more than 200 MRIs for brain tumor segmentation, also reviewed by our readers, and we also had a pretty heterogeneous data set with more than 160 high-grade gliomas and about 60 low-grade gliomas. You can see that the number of patients is not extreme, it's not super huge in this data set, but that is something that could be definitely used for training the model. And actually we used the ensemble of that kind of architecture. So we had a number of units that were trained over different training samples, and they were ultimately bundled into an ensemble to perform the final prediction, the final classification. Right, so I think we all know that if we want to have a look at the quality of segmentation, may have a big number of different metrics. So we can have a look at the overlap metrics, for instance, the dice score or the intersection over union, etc. So we have different metrics that quantify the overlap between automatic and ground truth segmentations. We also have some metrics that help us understand what is the distance between contouring. So for instance, we can use the Hausdorff distance to try to understand the differences between contouring that are automatic and ground truth, so manual. We can have a look at the volume of our tumor. We are again looking at the whole tumor, so the tumorous tissue within the brain. We can quantify the volume because we know all the numbers that are important and necessary to quantify the volume. We can try to track the volume and understand what is the difference between our volume and the ground truth volume that was calculated for the ground truth segmentation. But it might be actually the problem of showing clinicians that, for instance, the dice score of 0.8 is enough to get high quality segmentation. So based on the overlap metrics, it might be difficult to find the acceptance criteria that might be followed within our CE mark certification. So it is not trivial to find a good value of a dice score that would be just enough to make sure that the segmentation is of high quality. Because what does it actually mean that we have the dice score equal 0.8? Is it high or is it bad? What happens if we have a bad ground truth segmentation? There are a number of different things that might affect the numerical scores that we can see here. So we can also have a look at the segmentation. So we can have a look at the images. And I used to show this example where we have the original data. We have two segmentations, one ground truth segmentation and one that's extracted by Sens.AI. And actually people tend to say that the middle column might be Sens.AI because we can observe some jagged contours in the last row. So it is very unlikely that a human could find the contour in this way. So super accurate, very jagged. It might be not possible for a human. However, that is actually the ground truth segmentation. So if we compare with our software, we can see that the jagged contouring was actually delivered by a human, by some reader that was actually drawing and contouring that kind of lesions within the BRAS data. So we want to actually understand if the algorithm is ready. As I mentioned, we can have a look at the numerical values, which are difficult because we do not have clear acceptance criteria. But we can again ask our human readers to have a look at the segmentations and decide if the segmentation is of high quality or is it of low quality. Is it clinically useful or is it unusable? It couldn't be used because it could affect the patient. Again, we had a number of readers that were involved in the study. So we had 12 readers coming from 2 different institutions. And you can also observe different numbers of years of experience. So we have pretty experienced readers, like more than 10 years of clinical experience. And we have some raters that have just 3 years of experience. Again, we can show the segmentations that are automatic and ground truth, and we can ask them to score the segmentation according to a very simple and easy to understand scoring scheme. So we have, again, 1 to 4, 1 and 2 is not acceptable, 3 and 4 might be acceptable in clinical setting. If we have a number of test patients, we can just average the values for the scoring. So if we have 12 readers, we can just average the score for every single patient, and we can try to capture the average scores obtained for the test sets. Here we have some examples. We have the values for the BRAS ground truth data, for BRAS Sens.AI segmentations, and for our clinical data. So we have some clinical data which included 50 patients, 25 with high-grade and 25 with low-grade gliomas. They were never seen during the training procedure, never used for validation. They were just kept aside and used for testing at the end of the verification procedure. So we can see that if we look at the average, it's not very convincing. We can see that, for instance, for the clinical data, it might be a bit low. So we are oscillating about 2 and 3 maybe. We have some readers that are getting close to 3, but we are still below 3, which is not cool because 3 is the acceptable threshold. So we can try to think how to interpret the values from the readers, because we again have 12 readers. They will likely disagree with each other, but they will provide their view on the quality of the segmentation. So we did another experiment, and we again looked at the agreement between readers. We saw that in most cases they disagree. There are obviously some cases where they do agree, but we cannot assume that people will agree with each other. And what is more, actually, if we have one reader that would be given the very same image in day 1 and in day, for instance, 5, she will very likely segment it differently. So she will end up having a very different segmentation in one day and very different in the other day. So that is a big problem in a clinical setting, to make sure that the manual segmentation is reproducible. That's actually also the reason why we want to introduce and deploy that kind of software into clinical setting, to make sure that we can reproduce the numbers. We have a full reproducibility, and we know that if we have the same patient, we'll always quantify the lesion in the very same way. We'll end up having the same numbers for a given patient and for the same scan. Super important in practice. So we looked at the distribution of the cases. We have again 12 readers, and we wanted to understand how many readers would say that a given patient, a given case is just enough for clinical setting. Is the segmentation sufficiently good to be exploited in clinical setting? Here you can see that we have a number of readers that would say that this segmentation is above or equal to 3, and we can see that there are virtually no readers that would always say that a given case is always useful in practice. However, if we look at the middle of this plot, we'll see that there are some readers, for instance, 6 of the readers would agree that this segmentation might be useful in practice, and the same story for the clinical data. So we ended up having the acceptance criteria saying that if at least half of our readers agree that this segmentation is correct, we'll say that it is correct. So we ended up having an ensemble of readers that would ultimately agree on the quality of segmentation. And that was actually our take on having a CE marked software. We are actually successful, so we were awarded the CE mark, and that might be deployed in practice. However, it also shows that quantifying the performance of that kind of algorithms is not trivial. So we cannot just base on numerical values for a given data set, because this data set might be also of varying quality. So the quality of the data set might affect the numbers, and the numbers may affect the patients, which is definitely something that we want to avoid in practice. Finally, we know that it is actually becoming more and more practical to deploy that kind of software in clinics, and I think that is just the way to go, to make sure that the software can help us reproduce the numbers, make sure that we always have quantifiable and measurable characteristics of the tumors and tissue, and at the end of the day, we always have the reproducible characteristics of the patients that will help us track the patient response and observing how does he respond to the treatment. So thank you. That is, I think, the summary. We'll be happy to take questions.
Okay, great. Thank you, Jakub. Very interesting presentation as well. Are there any questions to Jakub, and maybe there are also some questions to Tomasz, then you can also try to ask. I don't see questions on our chat now, but let's maybe wait. As for now, maybe I'll just ask the first question, Jakub. So you presented a slide with the questions: are our models already good enough? So how do you think, if you have to just assess the current status of development of such deep learning models for let's say applications in radiology? So we already know that these models can potentially support the professional radiologists, but do you think that at some point they can just replace radiologists, or if so, how far we are from such state, and how do you think how this area may develop in the future, in the next years?
It's a very important question. I actually had not mentioned that, but in our case, that was just a supportive tool. So we use the software as a support to a clinician. So at the end of the day, the decision is always taken by a human. And that is actually the current state of the art. So we build the models or the software that can help us take better decisions, but they are unlikely replacing the human at the end of the pipeline. So we, to actually get and to reach to this point, we have a big number of challenges to tackle, starting from the validation, going through the actually proving that things can work and they are robust enough to sort of replace a human. I think it's unlikely in very near future in that kind of setting, because we are affecting patients, or we could affect patients, and that is actually a serious thing.
Okay, and how do you think? Do you expect that we can still significantly improve the current state-of-the-art models, or can we expect that there might be much better models in the future? So, for example, recently some models based on transformers outperform convolutional neural networks in some computer vision tasks. So how do you think how this domain may develop, and what we can expect in the future?
You're actually in a very interesting point, because if we look at this brain imaging, we have the BRATS competition, the BRATS challenge that is organized every year. And we can actually observe that there are some architectures that outperform other architectures. Those are most likely based on units. There is a framework called NNUnit, which actually is almost every year in top 3 algorithms. So we are currently building upon the unit architecture in 2D, in 3D, in some additional, I'll say, architectural changes within the unit. But fundamentally, we exploit units as much as possible. So that is the model that actually established the state of the art. We actually have some possibilities at the moment. We can have mixed precision training. We can have bigger models. We have a lot of things that we can do with the model to make it even better. And I think the important thing to remember is that the value is within the data. So if we have high quality data, we can build better models to generalize better and to actually help to have more accurate segmentation.
Okay, good. All right. Are there any more questions to Jakub? Yeah, it's really interesting how this domain may develop in the future. All right. So thank you, Jakub. It's a very interesting presentation, and it was the last talk today. So let me just share some ending slides. So first of all, thank you for your attention. I'd like to thank all the participants, and also thank once again our great speakers for being with us, for great talks. If you are interested in our events, we also invite you to join our Facebook group or mailing list on Google Groups. Follow our Facebook profile or YouTube channel if you have any questions or feedback, you can always send us an email. And after this meeting, we'll also send a survey to all the registered people. The next Warsaw.ai event will be hopefully in October. Most likely it will be still a remote only event, but we hope that in the next months we'll be able to just come back to stationary events as well. So we already invite all of you, and also feel free to invite some other fellow AI enthusiasts, experts, researchers. So we hope to see you next time during our next events. So thank you once again for your attention.